Hey, all you students of mathematics out there in YouTube land. Today we're going to do our second lesson in Unit 2 of Calculus. And in this lesson we're going to be talking about this relationship between a function and its derivative in respect to their graphs. Now last time I showed you this idea that you can create a function that represents the slope at any point along the curve. So if I give you a function and I say, what's the slope at any of those points, you could tell me by taking the derivative or getting the derivative function, right? And so there's this relationship that we see in calculus between a function, the graph of a function, and the graph of the derivative function. And so we're going to kind of just introduce that idea here. We go a lot more in depth as time goes on, but we're going to see some very interesting, cool relationships between these two functions that I hope you appreciate and I hope you understand. So with that said, let's go ahead and take a look at what we have here. We're going to be comparing f and f prime graphs, basically. Okay, so this is an activity that you can find it's a little half sheet of paper. You can do this actually you'll do that after this slide, but it says, in this case, it says plot the slopes of the tangent lines to the function on a separate graph. Now, if I have a graph, and we're going to call this graph f. This is the function f, and we have it go down and then up and then back down a little bit here. And we've got all these different points. We've got A, we've got B, we've got C, and then we have D here. I'm going to kind of continue that on. Okay. So this is the graph of f. Our goal is to be able to graph the function f prime, or the derivative of f, okay? So let's go ahead and take a look at what that kind of looks like. It might be a good idea to actually put it underneath it so you guys can see that correlation. This is going to be the graph of f prime. Now, before we can do this, we have to understand what f prime means. Remember, f prime is the derivative of f. But what's the derivative? The derivative is the slope of the curve at different points, or the slope of the tangent line at different points. And so as I go along here, as I go along the x-axis, I can identify different slopes. Now I can't identify all of them, but I can get an idea of certain very valuable ones. For example, when x equals a at this point, what kind of tangent line do I have? How would I draw a line that's tangent to that? Well, I would draw a horizontal line. And you can see that as that graph bottoms out and comes back up, the only line that makes sense as a tangent line is going to be a horizontal one, right? And so we would ask ourselves, what is the slope of that tangent line when x equals a? Well, the slope of that tangent line is 0. So when x equals a, the slope of the tangent line is 0. So that means the derivative's value is 0. Because remember, the derivative is a slope. We could write this off to the side if this helps. We could say that f prime of a is equal to 0. The slope of the tangent line of f at x equals a is 0. So we have a value for f prime. Now, as we go along here, we're not going to get really too detailed because we can't at this point. But if I were to look at b, and say, what is the slope at that point? Well, what is the tangent line? Now, the tangent line's kind of weird here because I would call this a point of inflection. It's where the curvature changes, and we'll get more into that in later lessons. But if I were to draw a tangent line here and ask, what is the slope of that tangent line? There's really no way of determining it at this point. But one thing we can say is that that line is increasing. That line has a positive slope. I don't know how positive, but it's some sort of positive value. So when x equals b, we know that the slope of the tangent line is positive, which means f prime will be some positive value. I don't know what it is. We're just going to go with that, okay? It could be anywhere in here, okay? Now at C, if I were to draw a tangent line at x equals c, you can see that I have another horizontal tangent line. So I can then say that when x equals c, f prime is again 0. F prime again is 0, okay? And then as I go further, if I look at point D and I draw a tangent line, I can see that that tangent line is going downhill, it's decreasing. And therefore, the slope is going to be negative. So at point D, at x equals d, we have a negative slope. So that means we are below the x-axis. So you can kind of see that relationship here. Now, in general, for right now, I'm just going to say this, that if you have a nice, smooth function, that implies that the derivative will more than likely be a nice, smooth function as well. So I'm going to go ahead and just connect these dots in a smooth manner. And we'll explore more of why in a later lesson, but for right now, I think this is reasonable here, okay? And then let's go over to maybe 0, or just to the right of 0, and draw a tangent line here. Well, we can see that that, again, is a decreasing line, so that means the slope will be negative over here, okay? And so we can see that maybe we have something that looks like this for the derivative. All right, so that's a good example of graphing a derivative function from the original function, looking at the original function's graph and graphing its derivative. Remember, all you're doing is you're looking for the slope of the curve at different points along the x-axis. And whatever that value of the slope is, not what the value of the function is, but what the value of the slope is where you just plot points here. Since that's 0, the slope is 0, we put a point at 0. Since that slope is positive, we'll put a point that's in above the x-axis. Since that's 0, the slope is 0, we put a point there. Since the slope here is negative, that means we're going to put a point below the x-axis, and so on. Okay? So that's kind of how you do it. We're going to look at more of a specific example here in just a second, so you can see maybe a little bit clearer on my end. Every time the slope is 0, every time we have a horizontal tangent line, we have the derivative hitting the x-axis essentially. All right. Now, with that said, let's go ahead and take a look at a pretty long problem here. It's a practice problem, but you should have a half sheet of paper, and your goal is to graph sine of x minus 1, and then essentially graph its derivative. Now I'm guiding you through this by saying, okay, draw the tangent lines of g at these different x values. Plot those slopes, plot the slopes of the values of the slopes of the tangent lines on a separate graph, and then smoothly graph that derivative function. Okay? And you'll notice something that's really, really cool. So go ahead and pause the video and do that, and then when you're done, come back, and hopefully you go, oh, whoa, that's really neat. And if not, then you'll say, oh, whoa, that's really neat, after I show you. So for this function, we've got g of x equals sine of x minus 1. Now I'm going to put parentheses around the x because I'm just taking the sine of just x, okay? Now we have a domain restriction of 2 pi to 2 pi, or sorry, negative 2 pi to 2 pi. So this graph should be pretty easy to graph, right? Sine function, sine starts at 0, and then it goes up, and then down, and then back up again. And it hits here at 2 pi, and it hits here at pi. And then over on the other side, it kind of does the same thing, right? I'm going to squish this a little bit just so I have more room. Okay, so that's, I guess, the best I got for you. But over here, we've got negative 2 pi, and we have pi here. And then obviously, the high point's going to be pi over 2, the low point's going to be 3 pi over 2, and all the points in between, thinking of your unit circle. Now, we want to plot the slopes, the values of the slopes, on a different axis here, okay? And so, what I want to do is I want to identify, well, it gave some very specific points at negative 3 pi over 2, negative pi over 2, and so on, right? And I'm just going to randomly pick one. Well, I can't say randomly because I know where this is going. Let's go ahead and plot the slope at this point, right? This is, oops, that should say negative pi. That's going to be negative 3 pi over 2, negative 3 pi over 2. At negative 3 pi over 2, what is the tangent line? Well, we can see it's a horizontal tangent line. So at negative 3 pi over 2, we have a 0 here, okay? Well, where else do we have a horizontal tangent line? That would be kind of nice to know. Well, we have a horizontal tangent line here, and here, and here. So let's go ahead and plot all those tangent line slopes on this graph down here. Well, this one is negative pi over 2, and then this one is pi over 2, and then this one is 3 pi over 2. So we know that we have slopes of 0 at negative pi over 2, at pi over 2, and at 3 pi over 2. So all the slopes are 0, and obviously this is going to repeat over time. So this is negative pi over 2, this is pi over 2, and this is 3 pi over 2. And if you have the graph, it's easier to see because it's on graph paper. All right, now let's go ahead and look at the other points, like negative pi, for example. Negative pi. Well, if I were to graph a tangent line at negative pi, we can see that that tangent line is decreasing, which means at pi here, or negative pi here, we're going to see that the slope is negative. See, the slope is negative. That means the value here will be negative. If the slope of f, or the slope of g in this case, is negative, then the value of g prime is negative. And I just realized I totally screwed this up. This is not the graph of sine of x minus 1. Sine of x minus 1 is shifted down 1. So I'm just going to fix that by getting rid of this minus 1, so I'm only looking at the sine function. We'll talk about why that doesn't matter in just a second. But let's go ahead and look at some other points. So like 0. If I were to draw a tangent line at 0, what do we see the curve doing? Well, we see the curve is increasing at 0, or the tangent line slope is positive, which means at 0 of the derivative, we're going to have a positive value. If this slope is positive, then we will have a derivative value that's positive. Well, at pi, what do we see as a tangent line? At pi, we see a negative slope. So at pi, we see a negative slope. Okay? And then we can look more at the endpoints. It asks us to do that. Actually, it doesn't ask us to do that. We can kind of do that because we know this continues on. At 2 pi, we can see that the function there is increasing, or negative 2 pi. So at negative 2 pi, we can say that we have another positive value for the derivative. Positive slope for the function means positive value for the derivative. And then over here at 2 pi, we can see the same thing again because we can say a positive tangent line. And now, so there's just some points that are plotted. And again, we're going to get way more in depth with this at a later time. But it says graph the derivative function by connecting the points smoothly. So if I graph this in a smooth manner, what do we see? This is really, really crazy, right? This is really, really cool. The derivative is the values of the derivative represents the values of the slopes of the original function. So if this is g of x, this function is going to be g prime of x. But notice what we have here. We know that if g of x equals sine of x, then g prime of x, look at that graph. What is that graph? That is the graph of cosine, the cosine function. So that's a really, really neat relationship that at first you wouldn't automatically go there, right? This is a nice, clean relationship that, to me, it just blows my mind that the derivative of something can be such a simple function and one that relates to that, the sine and the cosine. So we can put that to memory. That's the first thing that I want you to remember out of this, is that when I have sine, the derivative of sine of x is cosine of x, okay? That's the first thing I want you to remember. And we can play around with this with other trig functions and see what happens, okay? But let's go back for a second and talk about when I had the minus 1 here. So if I go ahead and look at a different function now, let's just say g of x equals sine of x minus 1. Well, what does that do to the graph? The minus 1, all that does is it shifts everything down 1 unit, okay? But what does it do to the derivative? It doesn't do anything to the derivative. Why is that? Because this minus 1 just shifts things down. Does that affect the steepness of these tangent lines? Does that affect this being a horizontal tangent line? If I shift everything down, that's still going to be a horizontal tangent line. This is still going to be a tangent line with a negative slope at that same point. So when I shift things up or down, it doesn't affect the values of the derivative. And so we can add to our ideas here that if I have a constant added or subtracted to the end of any function, that doesn't affect the derivative. Okay, that doesn't affect the end result of the derivative. So the derivative of sine of x is cosine of x, and guess what? The derivative of sine of x minus 1 is still just cosine of x. It's not cosine of x minus 1. Okay, that constant that was added or subtracted at the end doesn't do anything to the derivative. Okay, now I want to go a little bit deeper into what we notice. That's a nice relationship. That's something that we're going to use all the time in the future, but I want to see other relationships here. And so let's go ahead and explore this at a different kind of level. We would say this. We would say that when g of x, or when a function, let's just do it in general, when a function has a horizontal tangent line, then its derivative is 0. Okay? So horizontal tangent line, there, and there, so we can see that the derivative has zeros at those 4 places. Now that seems like kind of an obvious one. We kind of stated that. But here's one that's really important. Okay? When a function is increasing, what does increasing mean? Increasing means going uphill from left to right. When a function is increasing, well, let's look at one example of this. So we could see from negative pi over 2 to pi over 2. Okay, over that interval, we can see that this function is increasing. When a function is increasing, what do we see about the derivative? What do we see about the derivative here? We see this function going uphill from negative pi over 2 to pi over 2. What do we see from negative pi over 2 to pi over 2 here? Well, we see that this function is above the x-axis. What's another word for saying above the x-axis? We say positive. When a function is increasing, then the derivative is positive. Okay, this is a huge connection that we need to make here. Anytime you see a graph increasing, then the derivative of that graph will be positive. And so that helps us kind of understand how to graph derivatives a little bit more, because you can just look at this and say, okay, it's going uphill, it's going uphill, it's going uphill. That means every value here is going to be positive. Now, the specific values, we'll get into at a later time, but just in general, that's going uphill, so this is positive. Now, let's go on to the next statement we can say. Well, let's go ahead and identify those intervals. Where do we see g increasing? G is increasing from negative 2 pi to negative 3 pi over 2, and from negative pi over 2 to pi over 2, and from 3 pi over 2, I'm getting in the way here, to, well, wherever the next one would be. It would be pi over 2, or 5 pi over 2, I'm sorry. 5 pi over 2, and so on, right? Dot, 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 because sine functions go on forever, right? And then backwards too, we could go with that. But look at the intervals. From here to here, we see increasing. Well, over the same interval here, we see that g prime is above the x-axis. It's positive. From negative pi over 2 to pi over 2, increasing, we see positive. From 3 pi over 2 to 5 pi over 2, we see positive. Now, the next statement, we would say, kind of correlates with that. When a function when a function is decreasing, the derivative is what? Well, makes sense, is negative. Okay, and we can see that in our graph. We can see from negative 3 pi over 2 to negative pi over 2, over that interval, we see that this graph is heading downhill. It's decreasing. So if I were to draw a tangent line along any point along the way, all those tangent lines would be having a negative slope. And so we can see from negative 3 pi over 2 to negative pi over 2, we see that the derivative is negative. It's below the x-axis. Students tend to try and oversimplify it. They say, oh, that's going downhill, so this one should be going downhill. No, 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 no. Just because this is going downhill doesn't mean that's going downhill. If this is going downhill, this is negative. Okay? If G is going uphill, then G prime is positive. Not going up, but above the x-axis. There is a difference between saying something is increasing and something is positive, right? So think about that for a little while. So where do we see that, the graph of G decreasing? Well, we see that from negative 3 pi over 2 to negative pi over 2. And we also see it from pi over 2 to 3 pi over 2. Okay, so we can see here we're decreasing over those same two intervals. We're negative and negative. Now, a question that might be popping up in your mind, and it's something that, again, we'll address in the future, how do I know that that is the lowest point? How do I know that negative pi produces a low point here? Well, the idea is this. If I were to take a tangent line, and give me just a second, I'm going to get a ruler. If I were to take a tangent line along any point along this curve, so tangent line, let me do it above. Tangent line, tangent line, tangent line. What do you see? You see it's getting steeper and steeper and steeper. And then as we pass through negative pi, and I move on the other side of negative pi, we can see that the tangent line is now starting to flatten out again. So we can see that the tangent line is steepest at that point. Well, when you see the steepest of a function, right, wherever it's steepest, like a roller coaster, wherever it's steepest, you're going to see either the lowest or the highest points. Where is it steepest along this part of the curve? It's steepest at 0. So therefore, this is going to be a high point, okay? Because this is the greatest slope. Therefore, this will be the greatest value, okay? So that is kind of the idea behind graphing these things. So what do you notice about the graphs? Exactly what I've written here, and I'm going to kind of summarize that with you. And this is probably more of a clean graph here. Here is the graph of sine x minus 1. Okay, so there's the sine x minus 1 on the actual lesson. But if I look at the graph of G and I decide I want to plot those points again, where do I see the slopes, or what are the values of the slopes? Well, the value of the slope, negative 3 pi over 2, we see a horizontal tangent line, so we put a point at 0. At negative pi, we see that the function is decreasing. We see the function's decreasing, or the tangent line has a negative slope, so we put a negative value for negative pi. For negative pi over 2, draw the tangent line. We see we have a 0 tangent line, and then so on and so forth. And so you can see that the pattern holds true. Okay, and so we connect that with a smooth curve just like we did before, but again emphasizing the idea I said at the beginning, that minus 1 tacked onto the end just shifts the graph up and down. It does not change the steepness of the graph anywhere, and therefore it doesn't change the graph of the derivative anywhere. Okay, now if I were to move it side to side, that would change things, but up and down, no. Okay, so here are some conclusions that I hope you can draw from this and hope you understand these three main things. That when G is increasing, anytime you see a graph going uphill, then its derivative will be positive. Now I have a nice, beautiful chart that puts this all together that you'll see in the future. Okay, so an example of this would be from negative 2 pi to negative 3 pi over 2, and then negative pi over 2 to pi over 2, and 3 pi over 2 to 2 pi, and then so on. I only looked at the closed interval here, that's why I wrote it the way I did there. And then on top of that, since g is decreasing, we see that the slope is negative. Therefore, the derivative will be negative, or below the x-axis. All right? So that's from negative 3 pi over 2 to negative pi over 2. We see below the x-axis. Now look at this. From this point to this point, the derivative is not decreasing that whole time. It's decreasing and then increasing. But what is true? It's negative. It's below the x-axis. This is decreasing over that interval. This is negative over that same interval. Okay? And the last thing deals with this one. Okay? When you see, I guess it deals with this, what I wrote down is a little bit different. When you see the function change directions, so going uphill to going downhill to going uphill, and so on. Anytime you see a change in directions, one of two things can happen. It either means that the derivative is 0 at those points, so we can see it's changing directions at 1, 2, 3, 4 points. That means we have 1, 2, 3, 4 places where the derivative is 0. But notice in the parentheses, the orange parentheses, it says, or g prime doesn't exist. And we're going to get more into that in the future, but because I don't want to overwhelm you with too many ideas all at once. But you can see 3 main points. When a function's increasing, the derivative is positive. When the function's decreasing, the derivative is negative. When you see a horizontal tangent line, the derivative is 0. Okay? So with that said, let's go ahead and take a look at a practice problem here. And I want to approach this practice problem graphically. Okay? And then we'll talk about it analytically afterwards. All right. So we have the graph, or we have h of x equals negative x squared minus 2x plus 3. And we want to graph that. So I'm going to get an idea of what this graph looks like by going back to my Algebra 1 days or my Math 2 days, depending on what you took math in. You got negative x squared minus 2x plus 3. And I'm going to go ahead and factor this just to get an idea. So I got negative, I'm going to take out a negative, so I got x squared plus 2x minus 3. And then that factors to negative x and 3 and 1, positive, negative. Okay, so here we actually have zeros, so we can graph this. Okay, we can graph this. We have a 0 at x equals negative 3, and we have a 0 at x equals 1. Therefore, we're going to have an axis of symmetry at negative 1. And you can do that by figuring out negative b over 2a and all that. But if I plug in negative 1, I've got 2 there, negative 2 there, that's negative 4, positive 4. So 1, 2, 3, and 4. Just trying to get a pretty accurate graph. Okay, so I've got my parabola that looks something like that. Okay, now what do we want to do here? We want to graph the derivative. So you can see in my lesson here, I've got my parabola, and I just continued on here. Now I want to graph the derivative function. So let's go ahead and do that. Maybe taking cues from what we talked about in the last slide. Where is the derivative? Where is the derivative going to be 0? Where is the derivative going to be 0? The derivative is going to be 0 when we have a horizontal tangent line. So we can see that if I drew a tangent line at the peak there, it would be horizontal. And so what does that mean? That means the slope is 0. So at negative 1, I can put a 0 there. Now I'm going to just arbitrarily pick this point right here. What is the slope of the tangent line at negative 3? Well, the slope of the tangent line is positive. This line is increasing, so we should have a positive value there. And then what's the slope at x equals 1? Well, you can see that the tangent line is decreasing. Therefore, we have a negative value for the derivative. Okay? So we can see increasing over the interval from negative infinity to negative 1, we see this function's increasing. That means the derivative is all positive over that same interval. From negative 1 to infinity, we see that the h is decreasing, which implies that the derivative is negative for every value to the right of negative 1. Now, we're going to get more in depth with this idea later on. But notice this is something cool. So just like I told you before, you're going to want to know this. What's the derivative of sine again? It's cosine. The derivative of sine of x is cosine of x. Well, here's a new one. If I have a parabola or a quadratic, then the derivative of a parabola is a line. Look at that, a line. Now, this doesn't prove it by any means, so don't believe me just off of that. But you can see that it makes some sort of linear shape, or at least it holds to the idea that they're kind of in line. We'll prove it later. But look, a parabola, the derivative of a parabola is a line. When this is increasing, we see that the derivative is above. When this is decreasing, we see that the derivative is below. And so we can see the derivative function there, okay? All right. Again, these points are just kind of rough ideas. So, you know, maybe you could make the argument, well, shouldn't that be up there and then maybe this here, and then it's not linear anymore? That's possible, but I think in the next slide we'll be able to prove this a little bit more in depth. So what do we see? We see that h prime is negative. The derivative is negative. Where's the derivative negative? The derivative is negative from -1 to infinity, or for all x values greater than -1. Why is that? Because we see h is decreasing over that same interval. And then we could say that h prime is positive above the x-axis from -infinity to -1 because h is increasing over that same interval. And then we could see h prime is 0 at -1 because we have a horizontal tangent line when x equals -1. Okay? So hopefully you're kind of getting an idea of how that all ties together and how that works. Let's go ahead and take a look at this analytically using the definition of derivative. So we have h of x equals -x squared minus 2x plus 3. And it's asking, in this case, it says, when is h prime negative, positive, and 0? Well, we just kind of did the graphical approach to that, but let's do it analytically now. How could I show when the derivative is positive, negative, and 0? Well, the first thing we have to do is find the derivative. Remember, h prime of x is equal to the limit as h approaches 0 of h of x plus h minus h of x all over h. Oh, I probably should have used a different function name because this h in here and this h here and this h there don't represent the h function. Remember, h represents the distance between the 2 points, and we're moving one point infinitely close to the other one to get a tangent line, okay? But regardless, we're going to go ahead and plug in what we have here. So h of x plus h would be negative x plus h squared minus 2 times x plus h plus 3. So that's just this first part here. I'll put that in brackets. That's my y2. Now I need my y1. So my y1 is h of x, so it's just that. Negative x squared minus 2x plus 3 all over h. Boy, there's a lot going on here. There's a lot going on here. That's okay. Now we just need to simplify this all the way. Limit as h approaches 0. I'm going to expand that, and I'm going to multiply by -1 all at once. So that's negative x squared minus 2xh minus h squared for that one. We'll distribute the -2, so it's negative 2x minus 2h. And then we have our plus 3 there. And then I'm going to go ahead and distribute that negative, so that becomes plus x squared plus 2x minus 3. And that's all on top there. And then we'll divide that by h. And then we will simplify. And we should see a bunch of things simplifying here. We can see that the negative x squared and the positive x squared cancel out. We can see that the negative 2x and the positive 2x cancel out. We can see that the positive 3 and the negative 3 cancel out. And so I'm just going to rewrite this so it's a little bit cleaner. Negative 2xh minus h squared minus 2h all over h. And now you can see that all of those have a common factor of h. So we're going to go ahead and factor them out. So that becomes h times negative 2x minus h minus h minus 2 all over h. And then we're going to go ahead and reduce the h's and plug in 0 for h. So when I plug in 0 for h, I end up with negative 2x minus 0 minus 2. And so we have h prime of x. So there's our derivative function. And look at that. A parabola, produced a derivative that is linear. And so that was the proof, at least in this specific case here. Now the question is, in this problem, when is h prime negative, positive, and 0? Now I'm going to approach this the way that I normally do in calculus. There's a couple different ways of looking at it. Again, you can look at it graphically, but I want you to start seeing it a certain way. We want to know when h prime is positive, negative, and 0. Well, we're going to first figure out when h prime is 0. So we're going to set h prime equal to 0. We'll figure it out first. So 0 equals negative 2x minus 2. And then we'll solve that. So we'll add 2, divide by negative 2. And so we end up with x equals negative 1. So we know that h prime of x equals 0 when x equals negative 1. That's the first thing we know. Okay. Now, I am going to do I'm going to do a number line here, and I have my h prime. So this number line, the values below represent x values. The values below the number line represent x values, and the values above the number line represent h prime values. So maybe I should use a different color so that we can see that. H prime is green here. What is h prime when x is negative 1? Well, when x was negative 1, h prime was 0. We figured that out. Now, we're going to figure out the signs of h prime on both sides of this. Now, since this is linear, it's linear, and it passes through the x-axis once, right? That means on one side of that, it will be positive, strictly positive. It can't be positive and negative on this side, because that would imply that you have another 0, right? We'll get more into that in the future, but I'm going to just go ahead and pick any number I want for x to the left of negative 1. So if I plug in like negative 5, if I plug in negative 5 here, negative 2 times negative 5 is positive 10, minus 2 is positive 8, and so every value to the left of negative 1 is positive. And no matter what number you plug in, it will be positive. Now we'll plug in values to the right of negative 1. So maybe 7. If I plug in positive 7, negative 2 times positive 7 is negative 14, minus 2 is negative 16. So at least at 7, we have a negative value. But we know for every value to the right of negative 1 will be negative, okay? And I want you to think about this for a little while, okay? If that wasn't true, if you had another positive value on this side, then you would have a graph that was positive, at negative 1 to 0. It's positive, then it's negative, then it's positive again. Then it wouldn't be linear. That's a linear function. So we can see exactly this if we graph this. At negative 1, we have a 0, and then it's positive on one side and negative on the other. So this is a number line, and we actually approach a lot of calculus problems by visualizing the number line. It's very helpful. Okay. All right. Now we can answer the question. We could say that h prime is positive, where? H prime is positive for negative infinity less than x less than negative 1. And h prime is negative for negative 1 less than x less than infinity. All right, so that answers our questions that we were asking for. You can see the analytical approach to this. But remember, the idea here is just to get the signs on the number line to help us see it a little bit more. You could have done it different ways because this is linear. You could have solved it in saying, okay, 0 is greater than negative 2x minus 2. That means we were looking for when the line is negative, right? And then we solve it, so 2 is greater than negative 2x. So we're dividing by negative 2, so we get negative 1. We got to flip the inequality. So when x is greater than negative 1, then we are, h prime is negative. H prime is negative. And then we could do the same thing on the other one. All right, so that kind of wraps that problem up. Just a quick recap. So here's how I'm figuring out the derivative right there, right? The limit as h approaches 0 of the difference quotient, plugging in x plus h into each of these x's, and then plugging in x into each of those x's, which is the same, and then simplifying all that, and then getting a derivative function of negative 2x minus 2. And then we're going to go ahead and figure out when it's negative, when the derivative is negative by saying let negative 2x minus 2 be less than 0, and then solve that. So when x is greater than negative 1, or from negative 1 to infinity, and then positive when negative 2x minus 2 is greater than 0, and then solve that so when x is less than or equal to, less than negative 1, and then 0 when negative 2x minus 2 equals 0. We already did that. That's when x equals negative 1. So that's this one right here. Okay. All right, let's go ahead and take a look at one last exit problem here. It says find the derivative of the function y equals 2x squared minus 13x plus 5 and use it to find an equation of the line tangent to the curve at x equals 3. So what are we asking for here? Essentially, it says, okay, let me write it down here so we can do it. Y equals 2x squared minus 13x plus 5. It says, find the derivative of the function. So the first thing we have to do is figure out what y prime is. And then it says find the equation of the line tangent to the curve. So we need to find the tangent line when x equals 3. So these are our two goals here. We want to figure out the derivative function first, and then we want to find the tangent line's equation. So y prime is equal to the limit as h approaches 0 of f of x, it's not labeled f, but that's okay, f of x plus h minus f of x all over h. And so y prime equals the limit as h approaches 0. F of x plus h means we're plugging in x plus h, so that'll say 2 times x plus h squared minus 13 times x plus h, right, because we're still plugging it in here, plus 5. We're going to put that in brackets. That's my y2. My y1 is just the function itself, so that's going to be 2x squared minus 13x plus 5, and then that's all over h. All right, and then we're going to simplify all that. Y prime equals the limit as h approaches 0. And guys, you should be writing that out, limit as h approaches 0 on every single line. Go ahead and expand that, and I'm going to multiply by 2, so I end up with 2x squared plus 4xh plus 2h squared. Distribute the negative 13, so minus 13x minus 13h, and then plus 5. Distribute the negative, so minus 2x squared plus 13x minus 5, and then all over h. And if we did this right, we should see a bunch of things cancel out at this point. The 2x squared and the negative 2x squared. The negative 13x and the positive 13x. And the positive 5 and the negative 5 all cancel out. And so we're left with y prime equals the limit as h approaches 0 of 4xh plus 2h squared minus 13h all over h. Whew! We see the common factor of h, so we'll take that out. And in fact, I'm not going to show that step. If I factor out an h and then reduce the h, I'm going to be left with 4x minus 2h minus 13. We're just dividing h out of all those terms. Plugging in 0 to h now, y prime equals 4x minus 13. So there is my derivative function, 4x minus 13. You can see again, this is a parabola. The derivative is a line, right? So that verifies that one more time. And then we want to find the tangent line when x equals 3. Remember, to find a tangent line, we need a point and we need a slope. Those are the two things we need. Well, the point is when x equals 3. So we just got to plug 3 into that equation. Y equals 2 times 3 squared minus 13 times 3 plus 5. And then simplifying that, that's going to be 18 minus 39 plus 5. 18 minus 39, what is that? That's going to be negative 21 plus 5 is negative 16. So then my point is 3 comma negative 16. My slope is found when I plug in x equals 3 to the derivative. So we would say y prime equals 4 times 3 minus 13. So that's going to be 12 minus 13, which is negative 1. So y prime equals negative 1. So I have my point, I have my slope of my tangent line. Remember, if it was a normal line, you'd have to do the opposite reciprocal of this. But we want just the tangent line, so it's going to be y plus 16 equals negative 1 times x minus 3. And that is my tangent line. All right, so I hope that this lesson was enlightening. There was a lot of little things that we should have been able to go, oh, that's kind of neat. Number one, the derivative of sine of x is cosine of x. Number two, the derivative of a quadratic is linear, okay? And we'll develop more of that idea later on. And then number three, that anytime a function is increasing, its derivative will be positive, while anytime the function is decreasing, its derivative will be negative. And then anytime you have a horizontal tangent, then the derivative will be 0. And that often happens when you have a change in direction, like a maximum or a minimum. But that's not guaranteed. We'll talk more about that in the future. With that said, if you have any questions, please comment below. Otherwise, I will see you next time.